Okay, so let's unpack this. We're living in this era of just gargantuan context windows.
Absolutely.
In the last year, we've seen models like GPT and Claude just push their limits from a few thousand tokens to, I mean, the equivalent of a full novel. We're talking 100,000 tokens or more,
Which is theoretically an immense capacity.
theoretically.
But, capacity and utility are two very different things, and that's the real tension we're diving into today. The promise is that you can feed an LLM, say your entire legal brief, or a dense scientific paper.
Or just a massive stack of search results.
Exactly, and it will flawlessly find that needle in the haystack.
But
Does it?
exactly. Our mission today is to answer that crucial question, and we're basing this on the research paper Lost in the Middle. Do these state-of-the-art language models actually read and, reason reliably across the entire length of that huge input?
And the really shocking discovery here is that just having a bigger window doesn't guarantee the model can see every word equally.
Right.
We're going to get into some dramatic positional biases that they found in these leading models.
So it turns out they have these surprising, specific blind spots right in the middle.
Right into center.
This sounds less like a high-tech AI system and more like me trying to read a textbook at 2 a.m. Okay, so let's start with the basics. How did the researchers even establish this bias in the first place?
They set up a really precise experiment. They gave the LLMs tasks where they had to find a single relevant piece of information inside a really long block of text.
Okay.
Now, if the models were robust, if their attention mechanism worked perfectly, performance should be flat. It shouldn't matter if the answer is first, last, or in the middle.
And here's where it gets really interesting and where the results start to feel almost human. The data wasn't flat at all.
Not at all.
It formed this distinctive, dramatic drop-off in performance right in the middle position.
They call this the core finding, the U-shaped performance curve.
Mm.
The model basically succeeds at the edges and just fails in the center.
So if we're picturing that U on a graph, what are the two high points?
Okay, so the first one, top left of the U, is what they call the primacy bias.
Yeah.
Performance is absolutely highest when the relevant info is right at the very beginning of the input.
The first thing it sees.
Exactly. The model pays incredible attention to whatever it processes first.
And then swinging over to the other side, the top right of the U, the other spike.
That's the recency bias. Performance spikes again when the key information is at the very end of the context, right before the question it has to answer. It benefits from being close to the query.
Right. And the bottom of that U, the big dip.
That's the lost in the middle effect.
Mm-hmm.
And that's where your accuracy just tanks because the model has to go digging for information buried deep inside the center of that context block.
That is genuinely startling. That U-shaped curve, that pattern of strong beginning, strong end, fuzzy middle, that is the serial position effect. It's a well-known psychological thing in humans, right? With memory. We remember the first and last things on a list. But these models are built on transformers with self-attention. Technically, they should be able to weigh every token. So why are we seeing this very human failure?
That's the multi-million-dollar question, isn't it? It suggests that while the model can look at everything, the way it learns to prioritize things during training, especially instruction tuning, pushes it toward the easy stuff.
The low-hanging fruit at the beginning and end?
Yeah, it's prioritizing efficiency over being thorough when it's just overwhelmed with input.
Let's ground this in some of the actual evidence. The researchers tested this on something super relevant right now. Multi-document question answering.
Right. And for anyone building modern AI tools, this is the core of what we call retrieval augmented generation, or RAG.
So what was the setup for that?
It's pretty straightforward. The model gets a question and a stack of, say, 20 or 30 documents, maybe Wikipedia passages. But here's the critical part. Only one of those documents actually has the answer.
And the rest are just distractors.
Very relevant distractors. It's meant to simulate a real search result list. The test was just to move the position of that one correct document.
And the results were not marginal. Tell me again about GPT 3.5 Turbo's performance.
So when they moved the relevant document from that prime spot at the start to the worst-case middle position, GPT 3.5 Turbo's accuracy just plummeted.
How much is a plummet?
Over 20 percentage points in some of the longer contexts. That's a massive hit to reliability for any real application.
20%. So 1 out of every 5 correct answers just vanishes because you moved a file. But the finding that really made me sit up was the comparison to the closed book setting.
Oh, absolutely. This is the ultimate paradox. In that worst-case scenario, with the answer buried in the middle, GPT 3.5 Turbo's accuracy fell below its performance in the closed book setting.
And closed book means?
It means the model got no documents. It had to answer from its own internal pre-trained memory, and it was performing at 56.1%.
Wait a second. So if I'm building a system and I spend all this time and money to retrieve context for my LLM, the result could be worse than if I had just asked the model the question directly.
That's exactly what it means.
Yeah.
In that specific configuration, the context is actually making things worse. It's actively detrimental.
That is the definition of counterproductive.
It proves that context isn't automatically a good thing.
Yeah.
It all depends on placement. And then they tested the premium extended context models, the 16K version of GPT 3.5 Turbo, and the massive 100K Claude 1.3.
And did that bigger window solve the problem? Was their U-curve any flatter?
No. And that was the other crucial finding. These huge context models performed almost identically to their standard counterparts.
So just making the box bigger doesn't fix it?
Not at all. It's like buying a longer bookcase when you still only ever look at the books on the top and bottom shelves.
That really puts a damper on the whole industry trend of bigger is better. But okay, maybe the problem is the complexity, Natural language, technical Wikipedia articles, maybe the models get confused by all that semantic noise.
That's a great hypothesis. And so the researchers stripped all that away with a minimal test, synthetic key value retrieval.
Okay, what does that look like?
They basically created a huge JSON object, just full of unique, random UIEDs, these long, meaningless strings of letters and numbers.
Right.
The model's only job was pure lookup. Find the value for this specific key. It removes all reasoning, all language understanding. It's just a raw test of retrieval.
And did the U-shaped curve finally vanish?
For some models, yes. Claude 1.3 and 100K version did near perfectly across the entire context, which suggests the Claude models have a more robust retrieval mechanism, at least for simple symbolic stuff.
But I'm guessing not for everyone.
You're guessing right. GPT 3.5 Turbo and another model, MPT-30B Instruct, still showed a clear struggle in the middle positions.
So even on a dead simple task?
Even on a trivial task.
Yep.
It confirms that for these models, the issue isn't just linguistic complexity. There's a fundamental difficulty in accessing data stored in the center of a long sequence.
It's just wild how consistent that U-shape is. So what did the researchers identify as the likely culprits? Was it architecture or maybe the training process?
They looked at three big factors, starting with architecture. They compared the standard decoder-only models like GPT and Llama, which only look backward, against encoder-decoder models like Flan UL2.
Which can look both ways.
Exactly. They use a bidirectional encoder that sees the whole context at once.
In theory, that should just fix it, right? If it can see everything, position shouldn't matter.
And within its training context length, so 2048 tokens, it helped a lot. Flan UL2 was really robust, almost flat performance. But here's the kicker.
Uh-oh.
As soon as they pushed it beyond what it was trained on, that U-shaped curve came right back.
So bidirectionality helps, but it doesn't solve the core problem of generalizing to longer contexts. It's not just about seeing the info. It's about learning how to weigh it when things get really long.
Precisely. Next, they looked at query-aware contextualization. So usually the question is placed after all the documents. A decoder-only model has to read everything before it even knows what it's looking for.
So they flipped it, put the query before the document so the model knows the goal up front.
They did. And in the simple case, it worked wonders.
The key value task.
Yep. Near perfect accuracy for all models. It suggests that for pure lookup, knowing the key early is critical.
But I'm guessing that magic didn't carry over to the real-world RAG challenge.
Not really. This change only minimally affected the complex multi-document QA task. It helped a little bit right at the beginning, playing into that primacy bias, but it didn't solve the lost in the middle problem.
So it's not just about forgetting the question, it's the sheer complexity of reasoning over all that text.
That's right. And finally, they looked at the training itself, instruction fine-tuning.
Right, because instructions are usually put at the start of the prompt. Did that accidentally teach the model to have a primacy bias?
Great question. They compared a base model, MPT-30B, to its instruction-tuned version. And the base model already had the U-shaped curve.
So the bias is baked in before that.
It's inherent to how the model processes long sequences. And they saw another interesting thing with scale. Smaller Llama 2 models, the 7B1, were purely recency biased.
Only the end mattered to them.
Yeah, they really only focused on the end. The full U-shape, with both the beginning and the end, only showed up in the larger models, like the 13B and 70B ones.
That is fascinating. The architecture learns to develop two anchors as it gets bigger. Which I guess brings us to the practical side of this. If context can actually hurt you, is giving it more always a good idea?
And the research suggests it's a true trade-off. More information helps, but only up to a point. After that, you're just adding noise and increasing the chance the answer falls into that middle dead zone.
To quantify this, they ran one last case study on open domain question answering, a standard Arrajai setup, but they just varied the number of documents they gave it from 5 up to 50.
The goal was to see if you could just brute force a better answer by throwing more documents at the problem.
Yeah.
And they found that the model's performance just saturated, it plateaued, long before the retriever's recall did.
Meaning the answer was in the documents.
It was there over 90% of the time. But the model just couldn't find it because it was buried too deep, somewhere in document 21 or 35.
How marginal were the gains from, say, 20 documents to 50? Because that's a huge jump in cost and latency.
Negligible. It was about a 1.5% improvement for GPT 3.5 Turbo and just 1% for Claude 1.3. Think about that return on investment.
That's terrible. Massive diminishing returns. You're potentially tripling your context length and your API cost, making the user wait longer, all for a 1% gain. That's an unacceptable trade-off in production.
It completely changes the focus for builders. The goal isn't just about maximizing context capacity anymore. It has to be about maximizing the quality and placement of information inside that window.
So what are the actionable remedies then for anyone building a reg system right now?
The findings point to two critical strategies. First, you have to get serious about effective re-ranking.
Pushing the best stuff to the top.
Exactly. Exploit that strong primacy bias. If the answer is in the first 3 documents, your system will probably work. If it's in the 25th, it'll probably break.
And the second strategy?
Rank list truncation. You have to recognize that using fewer, higher quality documents is often safer and more cost efficient. If your re-ranker is only confident about the top 10, don't pass documents 11 through 50. You're likely just adding noise and pushing the model into that dangerous middle zone.
This has been a really eye-opening deep dive. So to summarize the key takeaways for you, the listener. First, these LLMs have a serial position effect, a U-shaped performance curve. They're good at the beginning and the end, but not the middle.
Second, just making the context window bigger, even to 100K tokens, does not fix this.
And third, in real-world retrieval tasks, giving the model too much context is a real trade-off. It increases cost and latency, and it can actually hurt accuracy.
So the requirement for the next generation of models is clear. To say you can use long context effectively, you have to show that performance isn't really affected by position. We need to see that U-curve flatten into a straight line. Until then, we have to treat long context with a lot of caution.
Which leaves us with an important question for you to think about.
Yeah.
The self-attention mechanism in a transformer is, in theory, equally capable of pulling information from anywhere. Yet we see this specific human cognitive failure, the serial position effect, emerge so consistently. If the machine is technically capable, why does it learn to adopt our inefficiency when it's faced with too much information? What does that tell you about how these models are actually learning to organize and prioritize in the face of an overwhelming world?